In this video, we shall find a sufficient statistics for P, given the PDF from a geometric distribution. So we are asked to find the sufficient statistics for estimating P. Solution. For me to find the sufficient statistics for the given distribution, we employ what is called the factorization theorem, which states that a statistics is said to be sufficient if it can be factored out into two components. What are the components? F of x as is given P is equal to, this is one of the components, say our T statistic, x1, x2 to xn. This depends on P. And the other component does not depend on P. So, this is one of the components from our factorization theorem. This is another component from our factorization theorem. So, given f of xp is equal to P, of course we know this is geometric distribution, x minus 1. Now we are asked to find the sufficient statistics for estimating P. The first thing to do is to take the likelihood function. Take the likelihood function. So we take the likelihood of the function here. So the likelihood function can be written to be the product sum as I ranging from 1 to n f of x p, which is equal to I running from 1 to n p into 1 minus p x minus 1. So we are not taking the product sum. That likelihood function we talked about is taking the product sum of the function given or of the PDF given. So the next thing to do is to take the product sum. The product sum for this, the first one will give us P, the first P, 1 minus P, and the first x, x1 minus 1, multiplied by P, 2, 1 minus P, x2 minus 1, multiplied by, we continue this place, P raised to the power of n into 1 minus P raised to the power of xi minus 1. So if it continues, we keep on putting values. So it continues to this point. So we can easily write our function to be P raised to the power of n into 1 minus P raised to the power of summation of xi's minus n, as I running from 1 to n, because this will give us n time, and this constant will also give us n time, because if we sum a constant we get n times that constant. So we get n multiplied by 1, but we can't write n multiplied by 1, instead we write n. So after this, we can now compare with what we have as the factorization theorem. We said for a statistics to be sufficient, each component need to be factored out into two. That means this part and this other part. So comparing with f of x p into e, we have our statistics, x1, x2, to xn, which depends on p, multiplied by x1, x2, xn. So this is one component, this is another component. So we move over to this other side of the board so that we can now compare it properly. For more on this topic, you need to subscribe to this channel. This is for the geometric distribution, finding the sufficient statistics. So we have our function to be f of x p to be equal to p raised to the power of n, 1 minus p raised to the power of summation of xi minus n, as I running from 1 to n. As we can see, everything we have here depends on p. What we have here depends on p, and this also depends on p. So we say multiply by 1. So in this, we have this as one of the components and this as another component. So this component will be 5p into our sufficient statistics, which is x1, x2, to xn. As it depends on p, and the other one is the other one here also does not depend on p. So the whole of this depends on p, while this does not depend on p. So we can also write this as, you say, or we write it as 5p to the summation of xi's as I running from 1 to n, because it's our mean, and this multiplied by h x1, x2 to xn. So it then means that our mean is a sufficient statistics for estimating p. So this is how we can find the sufficient statistics for estimating p. If we follow these procedures, it will be very easy for us to compute the sufficient statistics for any distribution. For more on this topic, you need to subscribe to this channel.